to demonstrate the basic usage of Homer using a simple probe. It's using simulated data, so you can also see the effects of a low-pass filter, high-pass filter, and block averaging. So the first step for us is to open MATLAB and run Homer 2. So as a start, we need to go to the path for Homer 2 and add all of the subdirectories of Homer 2 to the path, and I do that using this command down here. So that adds the whole path of Homer 2 to MATLAB. I can then switch back to the directory that has my data, and I'm using just a very simple probe data set, and also in this directory is a config file which contains the processing stream that we're going to be using to analyze this data. The exact details of the processing stream are covered in a different tutorial. So now that we're in this directory, we can run MATLAB, we can run Homer 2 using the Homer2_UI command. When we press return, and that initializes Homer 2, starts it up. It's asking me to choose a config file for the processing stream, so I have that here and I select it. You could have hit cancel and it would have selected a default configuration file for you. So now this is the basic layout of Homer 2. It gives us the probe geometry here, where the sources are letters. So we have one source, A, and it's surrounded by 4 detectors. So if we select the detector, it will show us the data for that detector with source A. Select detector 2, I get the other channel. Detector 4, I get the other channel. Or I could select source A, and I'm now going to see all channels of data together. We can right-click these individual channels and make them appear or disappear. Okay. So that's just turning them on and off, so it makes it easier for you to see different data sets. Okay. Another way, so another thing we can do is just left-click, and that turns it dashed and with a pink background. You still see the data, but the data has essentially been removed from the processing stream. Functions in the processing stream should ignore this data if you've manually selected it this way. This is important because there are some functions that will be adversely impacted by very noisy channels. So if there's a channel in your data set that has very poor SNR, no signal whatsoever, oftentimes it's good just to manually remove it from the analysis stream. There are functions that you can utilize as well that will automatically prune such bad channels from the analysis. If you want to make this invisible as well, you would right-click it as well. It now becomes dashed, and it's turned invisible as well as being excluded from further analysis. So I'm going to click and right-click this again so that it returns back to normal. So now let's look at the processing stream. So here we have a very basic processing stream. All it's going to do is convert intensity to optical density. It's then going to bandpass filter the data. It's then going to convert optical density to concentration. And then it's going to perform a block average. You can see you can mouse over these functions to get more details. You can also mouse over the parameters to learn more about the parameters and see typical values for those parameters. So this is a low-pass filter, and it indicates that typical values will be from 0.5 to 3 Hertz. Okay, so this is the processing stream. We can run this processing stream by selecting Run, and it runs the processing stream. It's a very simple processing stream. It's very fast. we can now look at the optical density, and you see that the optical density is displayed here. This is now the bandpass filter data. So if I come over here and reduce the bandpass, the low-pass filter frequency and rerun it, you're going to see that the data becomes much more smooth. Okay, that's the effect of a low-pass filter. You can also use this parameter here and change the high-pass filter, so I can make that 0.01 and run that. And you can see, in this case, what the effect of a high-pass filter is. Typically, you use a high-pass filter to try to do some drift correction. But if there's no drift in your data, or sometimes if you choose too high of a high-pass filter, it could actually have adverse impact on your data. These days, better ways of doing drift correction is actually to incorporate it into a grand linear model and simultaneously estimate the evoked hemodynamic response as well as the drift correction. So our next step is we convert the optical density to concentration units. So we can click down here and we can view concentration. So this is oxyhemoglobin. This is simulated data, so it doesn't look very special. The deoxy, is the same as well because it's just simulated data. If we shift click, we can view both oxy and deoxy at the same time, where oxy will be the solid line and deoxy will be the dashed line. Okay. So these vertical blue lines are the stimulus onsets. So there were 3 stimulus onsets presented during this simulated data set. And we're performing a block average of the response to the stimulus, and we're going to average from 2 seconds before the stimulus to 20 seconds after. So we can say, after we've done the block average, we can say, show me the evoked response. And this is the evoked response, the hemoglobin, oxyhemoglobin response. We shift click, and we can also see the deoxyhemoglobin response. Okay. If we change this time, we don't need to go to 20 seconds. We could just go out to 13 seconds. So I'm going to change 20 to 13, and I'm going to rerun this. Okay, and you see that's impacted now the time scale for our evoked response. We can come up here and we can view the HRF standard error. So this shows us the standard error that's estimated during that block average over 3 trials. Let's just look at oxyhemoglobin at this time. If we come back now to the data, we see we have this panel here. I can zoom in right now because I've selected zoom. So I can zoom in and I view the data. I can also select pan, and now I can pan through the data and look at different trials. Okay. I can reset this zoom. It shows me everything again. We also have this waterfall option. So I can enter a number here, let's say 2, and that corresponds to these units here. 2 now separates my data so you get a waterfall plot of the data. That can be helpful sometimes. Let me go back to the non-waterfall display. There's also stim reject. I can click that, and now I can manually remove stimuli from the averaging. So I can say toggle this stim off, and now it's dashed. So now when I rerun the processing stream, this trial is not going to be included in the trial average. So we can look at this evoked response, and you see that actually the error bars got a little bit larger, okay, because we're averaging only 2 trials now and not 3. Let me repeat that now. I'll come back here. I'm going to toggle this on again. So I'm going to make it included. It's a solid line. Let's look back at this. So we have large error bars with just 2 trials. I rerun the average, and you see now the error bars have gotten smaller because we're now averaging over 3 trials. Okay, so that introduces you to the basic operation of Homer 2, bandpass filtering, and block averaging.